So today we're talking about modeling with exponential functions. So how do you actually use them in the real world instead of just graphing them for whatever purpose? So without putting these in your calculator, pause this video and decide which of these are increasing and which of them are decreasing. Okay, so these first three are increasing. The reason being your base here is greater than 1. Then these three are decreasing because your base is less than 1. So it still has to be positive, but it's like a fraction or a decimal. This one is going to be growing the fastest because it's the largest base. And then this one is decreasing the fastest because it's the smallest base. Okay, so exponential functions. Here's our base, our general thing here. We have exponential growth when a is positive and decay when a is positive for both, so that's the same. The difference here is if b is positive, you're growing. If b is less than 1, you're decreasing. So this is a fraction or a decimal. Growth is going to look like this. Decay is going to look like this. Drawing the axes. So some examples. Here we want to figure out which of these is growth and which of these is decay, or what they are, and then figure out what's the percentage of growth or decay. So to figure out this percentage, we want the distance from 1, because 1 is like 100%. It stays the same. You're not changing. So looking at this first one, decide, is this bigger or less than 1? Well, it's bigger than 1, so this is going to be growth. And then we want to figure out how much more than 1 is it. So if we do 1 minus 1.08, we get 0.08 left at the bottom. And then turn that into a percentage, so your growth by 8%. Next one, here we're less than 1, so it has to be decay. And now again, we want the distance from 1, so this should be absolute value here. We want 1 minus 0.85, and you'll get 0.15, or right there. So you're decaying by 15%. So decay by 15%. Like that. So population model. You use exponentials a lot in like biology and other classes where you have populations. So how things grow, like how bacteria grows, how animals grow, all sorts of stuff. You usually use this general form, which is the exponential function in disguise. This would be your a, this is your b, and this is your x. So P of t is your population after some amount of time. So 10 years, 2 years, an hour, 5 minutes, whatever. And then P sub 0 or P naught is your initial population. So that's what you're starting with. R is your rate of change. So are you going increasing by 5%, decreasing by 2%? You always do 1 plus your increase or decrease, and then T is your time. So some examples with this. Here, Minnesota had about 1 million deer in 2016. If the deer population grew by 12% per year, how many deer would there be 10 years later, or in 2026? So we want to write out our equation. We want to figure out our population. We have 1 million to start off with. And then we're growing by 12%. So we're going 1 plus 0.12 or 0.12 to time. So then if we want to answer the question, we can just plug in 10. So P of 10, we have 1 million times 1.12 to the 10. Type that into a calculator and you'll get 3,105,848 deer, rounded to the nearest deer since you can't have half a deer. Well, that's the idea. Okay, so next one here, we have plutonium has a half-life of 24,100 years. Suppose a sample starts with 500 grams. We want to write this function. So same idea, you could say P of t or y or whatever you want. So 500 is your initial amount. And then this is a half-life. So it's saying when we get to half of that. So since it's a half-life, our rate is a half, or you could do like 1 minus a half since it's decaying. You'll still get a half. And then our time here is a little weird. We have to divide by our 24,100 years because we want to get 250, so half of 500, when we're at x equals 2,400, 100 years. But if I just do x, well, then we're going to get to 250 at 1 year. We don't want that. So this scales it. So when x equals our 2,400 or our half-life, then y equals 250. Okay, so next we want to use your calculator to estimate to the nearest 1,000 years how long it will take for the sample to decay to 100 grams. So 100 grams, that's when y equals 100. We want to know when x equals. So graph this function right here. So I go to the calculator, we can type that in. Go to y equals 500, and then times 0.5 to, and you'll need parentheses here, your x divided by your half-life. And that's your function. And then we want y to equal 100, so put y equaling 100 in there. Hit graph, and wait for it to show up. Here we're not seeing anything because we're starting at 500. We're now at like 0 to 10 and 0 to 10 for our x's and y's, so we need to zoom out. So if you're using your calculator, you need to adjust the window. So hit window. We know y starts at 500, so I'm going to start at go to 510, so I'm a little bit above it. And then we're talking about thousands of years here when we're talking about our x's. So let's just make this like 60,000 and see what happens. Okay, so now here we can see what happens. The blue line is our exponential. The black line is our, whatchamacallit, like what we want it to be. So I'm going to adjust this again and have a little less x's so I can see a little better. Let's make this like 50,000 and graph again. Okay. And then let's change the y so we're not quite so big. I'm just trying to do this to get a good picture, so it doesn't really matter exactly what you do, but I want a decent picture so I can find my intersection. So now you want to find the intersection, so you want to get this calculate button up here. So do second trace to get your calculate, and then we want the intersection. So do 5 to get the intersection. And then this is like we did for zeros. You want to be on the left side of your intersection and then the right side. So it looks like we're intersecting like right about here-ish. So I'm going to say that we're on the right or the left side. Then I'm going to arrow over past where I think the intersection is. So I think the intersection is right there. I'm going to arrow over past it, hit enter. All right, so then after you've hit the right bound, you're going to have to wait a while for it to actually work. And then it will give you your little mark here and tell you where they intersect. So it's saying about when x is 57,125. So if you keep that number in mind, go back to here. Our question was, what was it to the nearest 1,000 years? So you're going to get x is about 50,000 years for that. You can actually just solve this equation by hand, but we're going to talk about that later. So later in the chapter, once we've talked about logarithms, we'll talk about actually solving these. So another example here, we're given that the bacteria in the petri dish after t hours is given by this equation. Again, we want to figure out how much time it's going to take to the nearest tenth of an hour. So we're going to have to adjust our window from last time for this population to double in size. So if we start with 400, we want when y equals 800. So now hop back to the calculator here. Go to y equals, clear this, change this to 800. Then we're going to type in our 400 and then e to the x. So to get that, that's down here above the ln, so the blue button, e to the x, and we got 0.41 x. and graph. And this is going to be weird. We're not going to see it because our window is messed up from the last thing we did. So go to the window. We want to see when x is 8 or y is 800. So I'm going to do like 850 for my max, and then be close to this. Let's start with like 600. And we're going to the 10th of an hour, so this has got to be pretty small. So I think we'll just go back to our standard 10 here and see what happens. So looking at this, I'm still not seeing anything. So I'm going to zoom in farther, go back to your window. I'm going to go up to 5 this time. And hit graph. Okay, so now we can see the intersection here. So do your second, calculate again, 5. You want to be on the left side, and then you want to be on the right side. And then here it gives you your value. So about 1.7 if we look right here at our value. So our answer to this would be when t equals about 1.7. And again, this is not 100% accurate because you're guessing, but that's okay. We're going to learn how to solve these later. So then here's your assignment. And let me know if you have questions.